All right, we're gonna pull back the curtain on one of nature's most effective secret weapons. It's a microscopic suit of armor that turns a simple bacterium into an incredibly tough opponent.
I mean, just think about that for a second. How can one tiny cell outsmart and defeat an entire immune system? Well, for over 100 years, scientists have been trying to figure that out. And it turns out the answer often comes down to this secret weapon, a nearly invisible suit of armor that makes some of our most dangerous pathogens so powerful.
And this is not just some simple shell. No. This is a super sophisticated piece of biological engineering. That halo that Louis Pasteur saw all the way back in 1881, that's one of the most effective tools a bacterium has for surviving inside a host, which, is us.
So we know this armor is a thing, but what exactly is it made of? And what makes this invisible shield so ridiculously good at its job?
I love this analogy. It's a suit of armor for pure protection, an invisibility cloak to hide from our immune system, and a sticky grappling hook that helps it latch onto surfaces inside our bodies. It's this incredible multi-tool that makes it so hard to get rid of.
What's really wild is that there's no single blueprint for this stuff. Most bacteria build their armor out of long, complex chains of sugars. Scientists call them polysaccharides. But then you have others, like the one that causes anthrax, that use proteins instead. It just goes to show you, evolution has found more than one way to build a really effective shield.
Okay, so how does this armor actually get built? Well, it is definitely not a random process. It's more like a highly organized manufacturing operation, with 3 master blueprints working at the molecular level.
So bacteria use one of these 3 main molecular assembly lines. They build the capsule components inside the cell and then ship them to the outer surface. You can think of them as different factory models that all produce the same thing. The fact that there are multiple ways to do this tells you just how vital this armor is for survival.
And the most common assembly line by far is the WZX/WZY pathway. It builds the capsule in repeating units, almost like snapping together Lego bricks, one by one. This is a complex, genetically controlled process, and it's the go-to method for over 90% of pneumococcus strains which cause pneumonia. Just picture that, a microscopic assembly line, perfected over millions of years, building a shield, brick by brick.
All right, we know how it's built. Now for the main event. What can this armor do? Let's get into its superpowers, because this thing is an incredibly versatile weapon.
Yeah, this is not a passive shield that just sits there. It has several active functions. It blocks immune attacks, it helps form these impenetrable colonies, and it can even fend off antibiotics. It's basically an all-in-one survival kit for invading a host.
This is probably its most famous trick. See, our immune system works by recognizing specific molecules on an invader's surface. But the capsule acts like a physical blanket, hiding all those telltale signs. It literally stops proteins, like one called C3b, from tagging the bacterium for destruction. It's like the bacterium becomes completely invisible to our body's security system.
Bacteria are kind of social. They rarely live alone. They love to form these communities called biofilms, which are a massive problem in medicine, especially on things like medical implants. And the capsule? It often acts as the glue, helping these bacterial cities get started and making them incredibly tough to clear out.
But of course, science is never that simple. Researchers are actually still debating the capsule's exact role here. Is it the glue that holds the biofilm together, or is it more of an escape hatch that lets bacteria break off and start new colonies somewhere else? The answer is probably both, depending on the situation. It just shows you how complex these microscopic systems really are.
And if hiding and sticking around weren't enough, get this. The capsule can also fight off our best weapons. That dense mesh of polymers can physically block some antibiotic molecules from ever reaching the cell. It just adds another dangerous layer to the huge, growing problem of antibiotic resistance.
Okay, so this is all fascinating microscopic stuff, right? We know what the armor is, how it's built, its superpowers, but why does any of this detail matter to us, really? Well, because it has a direct and sometimes deadly impact on our health.
This is where it all connects back to real-world diseases. Just like there are different models of a car, there are different models of these capsules. They're called serotypes. And a tiny little tweak to the chemical recipe can be the difference between a serotype that's pretty harmless and one that's extremely dangerous.
93. Just let that number sink in. That's how many different capsular serotypes have been identified in just one species, Streptococcus pneumonia. 93 different suits of armor, and almost all of them can cause an infection. It's just a staggering amount of variety.
And this chart makes the connection crystal clear.
Look at E. coli. Equip it with a K1 capsule, and suddenly it's a major cause of meningitis in newborns. Or take Klebsiella pneumoniae. Its K1 or K2 capsule is directly linked to these severe, life-threatening liver abscesses. The specific type of armor often determines the specific kind of threat.
But here's the craziest part. Just when our immune system finally learns to recognize one type of armor, some bacteria can just switch it. They change their armor. It's called capsular switching. It's like a fugitive changing their appearance to escape the police. It is a live-action, high-stakes, evolutionary arms race happening inside our own bodies. So because these capsules are so absolutely crucial for causing disease, they have also become our #1 target for preventing it.
The whole idea behind many of our most successful vaccines is actually pretty brilliant. Instead of just targeting the bacterium itself, we train our immune system to recognize its armor. Vaccines like the one for pneumococcus teach our bodies to spot these different capsule types. By targeting the armor, we can neutralize the threat before it even gets started, giving our bodies a real fighting chance.
But that race is not over, not by a long shot. Bacteria are constantly evolving, switching their capsules, developing new ones. So the ultimate question really remains. As they keep upgrading their armor, how will we upgrade our defenses? It's a battle of adaptation, and frankly, it's one that will define the future of medicine.